We discussed this problem by proving these two cases by equating the domain of these two functions equal and codomain of the two functions are equal. Then we can say those functions are equal. In that way we proved that. So we can also follow the other method. See, given that f is a bijection is given, so according to that f is bijection is given. So we know that bijection means it follow the one-to-one function, one-to function. If f is a to b, I can also write the f inverse b to a. Okay. Then identity functions also we need it now to prove this one. So identity function of a, we can write a to a. Identity function of b, we know that b to b. F is the bijection. F is a bijection. Then it is the onto function. I can write like this now. I can take the x comma y or belongs to the set A and set B elements. Okay, na? X belongs to the A set element, y belongs to the B set elements. Then I can write this equation. Why? Because f is the bijective, means it is the onto function. Then when it is the onto function, we can write this relation. Why? Because this is the image values. Okay, na? So these image values are corresponding to the each element in the set A. That's why we can write f of x equal to y. We can write it. Similarly, f is bijective. F inverse also a bijective, compulsory. That's why we can also write we know that B set elements we can represent with the y, A set elements we can represent the x. Now I can write f inverse y, which is equals to x. Why? Because here x is nothing but image. F inverse y is nothing but, here what is the y is nothing but domain. Okay, na? For each domain value there is a corresponding image value. That's why we can say f inverse also, because of f inverse also bijective. We know that identity function is a bijective function. We can write like that, I of x is equals to x. We can write it. IB also a bijective function, and which means it is onto function. We can write like this. It is onto function. F of y is equals to y. We can write it. Okay. From this we can prove that two functions are equal. Now I am taking the first function. F circle IA. I am going to prove that function is equals to the function of f. See, function of f circle IA. I am taking the input function, input value is x. Now I am applying I am expanding this composite function by removing the circle and placing the bracket. Okay, na? And plugging the bracket. In the bracket we have to write the identity function. We know that in identity function, how can you write it? According to the bijective, we write it follows the onto function. In IA of x also we can write it x. This is IX we can replace by x. We proved that f circle I of x, we proved that which is equals to the function of x. Then we can say f circle IA which is equals to the function f. Similarly, second case B part. This is the B part. See, f inverse f, you take the input x. Okay, you are taking the input domain values. You take the x values. Now I am applying expanding the composite function, remove the circle and then plugging in the bracket for the function f of x. Okay, this I can represent with the f of x. We know that f of x is y according to the bijective rule. According to the bijective rule, we can write f of x is equals to y. We know that according to the bijective rule, f inverse y is nothing but x. F inverse is nothing but x. We know that it is onto function. In place of x, I can also substitute the identity function of x. Then see, this f inverse of x, we can write the identity function of x. That's why these two are equal. In this way also we can prove these two